Welcome back, everybody. Mr. Klinkerman here. We're going to talk now about how you graph a quadratic function, which is a shift in the focus from the first half of the chapter where we were solving quadratic equations through the use of factorization, completing the square method, and the use of the quadratic formula. Okay, now we're graphing quadratic functions, a different focus altogether. And you can see in the first learning goal for this section, we're going to look at a graph of a quadratic function whose equation is written in standard form, y equals ax squared plus bx plus c. And there's a certain method you'll use to graph a quadratic function when its equation is written in that form. And then in the next video, for learning goal 2, we'll look at a quadratic function whose equation is written in turning point form, which is right here. And we'll learn the method for graphing a parabola when its equation is written in that form. And if you remember what we learned about horizontal and vertical translations in the last chapter, you'll already kind of understand that form just from looking at it. And then thirdly, there are 3 learning goals in this section. We're going to look at when a quadratic function's equation is written in factored form, and hopefully you recognize this as factored form. And we'll see how do you make the graph of the quadratic function from that form of an equation. Where I'd like to begin here is just by talking about specific properties of a parabola, though, which is what the graph of a quadratic function is called, is a parabola. You knew that already. And over here I've got just some random graph of a parabola that I'm going to use to explain some of these special properties to you. Now, I'm going to list these properties and kind of point them out with an arrow, and then I'll draw them on the diagram just to make sure we're clear about where these features of a parabola are. All right, key features of parabolas. And one of the key features of parabolas, and this is super important to making the graph easy, is that it has symmetry. And I think you can see or imagine me drawing a line of symmetry right here. And then this half of the graph and this half of the graph would be reflections of one another in that line. A second key feature of the graph of a quadratic function is its vertex, which is also known as a turning point. All right, and I think you can see how this would be the most distinguished point on the graph compared to the others. I guess there's a few points that are distinguished from all the others. This is the lowest point on this graph. Vertex can also be the highest point. And you can see it's just where the graph switches from decreasing to increasing. That's why it's called a turning point, as well as the vertex, like you're familiar with. And then some other key points that would be on the graph of a parabola. Whenever a quadratic function has x-intercepts, those are key points that you can use to help you with the graph. And every parabola is going to have a y-intercept, and so that's a key feature that can help you make the graph of a parabola. Okay, and I said I was going to draw those in. Let me do that real quick. Okay, so right there is the axis of symmetry, and you can imagine how this half of the graph and this half of the graph are reflections in that vertical line that I just drew. Okay, and that point that I just made in orange would be the vertex or the turning point. And then of course those 3 red points that I made, those would be the x and the y intercepts. Those are the key features you're looking for every time you're trying to graph a parabola. Alright, now next I'd like to show you a cool relationship actually. You may have seen this before, but I doubt it. And the relationship I want to show you is that between the quadratic formula, which we've been studying in section 2.3, and the graph of a parabola. All right, and I've made up a specific equation this time to illustrate what it is I'm going to try to show you about quadratic formula versus the graph of a parabola. Okay, now we said that one of the important features for a quadratic function's graph is its axis of symmetry, right? And then another pair of important features are the x-intercepts. And it turns out that the quadratic formula is something you can look at, and it will show you where the axis of symmetry is, and it shows you, or helps you determine anyway, where the x-intercepts are. And I'm going to break up the quadratic formula into 2 parts. I'm separating the opposite of b over 2a from the square root of b squared minus 4ac over 2a, because these are this and this show those 2 things that I just explained. Now I'm going to draw this and color code it for you so you can follow what I'm talking about. First of all, the opposite of b over 2a, it turns out, is how you determine where the axis of symmetry for the graph of a parabola is going to be. Alright, that's the axis of symmetry. Then, this portion right here, the square root of b squared minus 4ac over 2a, what it actually tells you is how far each of the x-intercepts is from the axis of symmetry. Alright, so that portion right there tells you the distance between the axis, meaning the axis of symmetry, and the x-intercepts. Okay, now here's what I'd like to do to show you how that works with the equation that I made for you. If I set that equation equal to 0, which is what you would do if you're trying to find the x-intercepts, you set y equal to 0, and then I plugged -1, 5, and -4 into the quadratic formula, but into this form right here, here's what you'd end up with. Alright, down here at the bottom of your screen. The opposite of b is -5, a is -2, or twice a would be -2, and -5 over -2 would be the same as +5 halves. And look at the graph. The axis of symmetry is the vertical line, x equals 5 halves. Okay, and then if you do your b squared minus 4ac, the discriminant ends up being 9. And of course, the square root of 9 is 3. 3 divided by 2 is 1.5. Okay, so the square root of b squared minus 4ac over 2a is 1.5. And that's exactly how far this point is from the axis of symmetry and how far this point is from the axis of symmetry. This is 1.5 and this is 1.5 as well. Okay, now I told you that because I want to help you remember something, and the major thing that I want you to remember is how do you find the axis of symmetry for a quadratic function when it's written in standard form, ax squared plus bx plus c. And that's what we're getting ready to look at so far. Now if you have any questions about all these concepts of the graph of a quadratic function, you should maybe rewind the video right now before we move on. If you're good with everything that I've discussed so far, then let's go ahead and move on. Okay, and here's another generic graph of a quadratic function with all the key features labeled. I've got, or at least pictured. There's the axis of symmetry, there's the vertex, there's the y-intercept, there are the x-intercepts. And I want to talk about how you find those key features when the equation is written in the form of y equals ax squared plus bx plus c. And when the graph of a quadratic function has its equation written in that standard form right there, well, the first thing we're going to try to do to make the graph is find this axis of symmetry. Okay? And what we just saw is that you find the axis of symmetry using part of the quadratic formula. You use this equation, x equals the opposite of b over 2a. Alright, you just saw how that works. Well, then the next thing that we're going to try to do is we're going to try to figure out where is the vertex of that quadratic function. You always have to know where the vertex is when you're graphing a parabola. Now, I hope you notice this, that the x-coordinate for that vertex has to match up with the equation for the axis of symmetry, right? Because that axis of symmetry is always going to go right through the vertex, and it's going to tell you what the x-coordinate for the vertex is. And so the vertex is going to have an x-coordinate and a y-coordinate, right? And the x-coordinate has to be the opposite of b over 2a. And the y-coordinate for the vertex. Well, anytime you're trying to find a y-coordinate for an equation, for a given x-coordinate, what you do is you plug that x-coordinate into the equation for that graph. And when you do that, you say you're finding f of x, or f of 5, or f of 9, or whatever you're plugging in. So the y-coordinate for the vertex here we can find by plugging in the x-coordinate for the vertex, or in other words, by plugging in the opposite of b over 2a. So then the y-coordinate for the vertex would be f of the opposite of b over 2a. Okay, if this doesn't make sense right now, you're going to see it in action here on the next slide. But find the x-coordinate for the vertex, plug it in, find the y-coordinate. I need one more set of parentheses there, don't I? You couldn't see that. Oh, there it is. All right, great. Then there's one last thing that you got to be able to find, or rather that I should say makes graphing an equation quadratic function easiest. Now it's kind of long in writing, but it's not so long whenever you're actually trying to do it. The third thing you try to do whenever you're trying to make the graph of a parabola from a standard form equation is you find the coordinates of any point that's not on the axis of symmetry. Okay, you need some point that's not on this line right here in order to make the rest of the graph. And then what you do is you take advantage of the symmetry of the parabola and you reflect that point in the axis of symmetry and sketch the parabola. All right, now that other point that you choose to find can typically be one of these things right here. It can either be the y-intercept, and if it's a y-intercept and you figure out how far the y-intercept is from the axis of symmetry, then you can reflect it and find out another point and then draw your parabola through those 2 points. Or you could find the X-intercepts, okay, using quadratic formula or whatever you want to use, and then you can draw a parabola through the X-intercepts and the vertex, and there you would have your parabola. All right, so you've got kind of choices. Let's see this in action now. We're going to sketch a graph of this function right here, y equals negative x squared plus 5x plus 3, and I'm going to do that using the order that I just described to you. I'm going to find out where the axis of symmetry is, I'm going to find the vertex, and then I'm going to typically find the y-intercept instead of the x-intercepts because it's super easy to find the y-intercept. Alright, our axis of symmetry is going to be x equals the opposite of b over 2a. And the opposite of b is going to be positive 5. 2a is going to be negative 2. So we could say that negative 2.5 or negative 5 halves is where the axis of symmetry is going to be. Alright, I'm going to change that graphing background so this will be a little bit easier to sketch from here. So let me go ahead and draw my coordinate plane. And that dashed line that you see is the axis of symmetry, x equals negative 2.5. Okay, the next thing we're going to do is we're going to try to figure out where along that axis of symmetry the vertex is located. And so to do that, we're going to plug in negative 2.5 into the function. That'll be the x-coordinate for the axis of symmetry, and that will give us what the y-coordinate for the axis of symmetry is. I'm going to go ahead and show the work. I can rely on you to use your calculator or whatever to confirm this result. Okay, now it turns out that f of negative 2.5 is 9.25. So the vertex then is going to be the point negative 2.5 comma, whoops, that wasn't exactly a comma, comma 9.25. Now real quick, I'm going to change my intervals on my y-axis now that I know how high the vertex is. I'm going to go by 2, so that would be 4, 8, 12, and so forth. And so negative 2.5 comma 9.25 would be pretty much right here. Alright, it's an approximation anyway. Alright, and then I either want to find the y-intercept or I want to find the x-intercepts. And the y-intercept turns out to be super simple to do, so that's what I'm going to find is the y-intercept. There's only one kind of scenario where you don't use the y-intercept really, since it is the easiest. Now the y-intercept, of course, is going to tell you where the graph crosses the x-axis, the y-axis, and x is always equal to 0 for the y-intercept. So what we're going to do is we're going to find out what f of 0 is. And that's super easy mental math because if you look at the equation, if you plug in 0 right here, that term becomes 0, this term will become 0, and then you have 0 minus 0 plus 3, which is equal to 3. Alright, f of 0 is equal to 3, and so the y-intercept is going to be 3. And I can go ahead and graph it right there. Alright, and then finally I'm going to use symmetry in order to determine how to make the rest of the graph. And here's what I'm going to do. I'm going to see how far is it from the axis of symmetry to the y-intercept that I just graphed, and it turns out that that's 2.5 units there, right? And so what I want to do is I want to go 2.5 units to the left. And if I'm going 2.5 units from negative 2.5 this way, well, here's the half, here's 1, there's 2. We're going to end up at negative 5, 3. Right, there's negative 5, 3. It's also 2.5 units away, so that's correct. And then I'll go ahead and graph the parabola. I've got enough points to do that. Just kind of draw your curve. It goes through your intercept and the vertex. Make sure you put arrows at the end because that graph is going to continue past what you see. That's how you graph an equation whenever it's written in standard form. If that makes sense to you, I've got one more example here that I'd like you to try on your own, and then you can watch a video to confirm that you really have this down. If it doesn't make sense, you might just watch me all the way through the next example. I don't have a third example though, so I'd rather you try this next one on your own. Alright, and here's the next equation that I want you to graph. Alright, try it out. You'll hear from me in a couple minutes to see if you got it right or not. Alright, first for the axis of symmetry, I did the opposite of b over 2 ways. So I did negative 6 over 8. And negative 6 over 8, same thing as negative 3/4. And I'll go ahead and graph that axis of symmetry real quick. There is x equals negative 3/4. Then of course the next thing is to find out where the vertex is along that line. So here's that. Right, if you plug in negative 3/4, you get negative 13/4. You can use your calculator to help you out with that. And so as a decimal, which is kind of helpful for knowing where to graph, you get negative 0.75 comma negative 3.25, which is right here. Okay, and then the last thing that I'm going to do is find the y-intercept. Right there at 0, negative 1, and reflect it in the axis of symmetry. Now when you do that reflection, of course, you see how far was that intercept from the axis of symmetry, and that was 0.75, and then you just go that same distance on the other side of the axis of symmetry, so I went 0.75 to the left, and that got me to negative 1.5. Alright, using the decimal, negative 0.75 minus 0.75 is negative 1.5. Then draw your parabola through those key points that you made. There is a graph of your parabola. Put my arrows again. Done, right? Okay, now the only time I would do something slightly different whenever I've got standard form is if the vertex ended up being somewhere on the y-axis itself, because then the vertex is the y-intercept, and so you'd have to find something to the left or right of it. But we'll tackle that bridge. I don't know why you would tackle a bridge. We'll tackle that problem whenever you get there. All right, well done. I'll see you next time.